Hello, wonderful people! Here we are in the chapter 36, Magnetism. So we're starting at the beginning with, and what is magnetism? A moving electric charge is surrounded by a magnetic field. So ultimately, all magnetism comes from a moving electric charge. But that's actually a pretty sophisticated idea. We don't actually talk about that electric charge part until section 2, 3, or 4. So let's stick with the basics for now. Section 1, magnetic poles. Like poles repel, opposite poles attract, just like electrics, right? Magnets exert forces on one another. They are similar to electric charges, where they can both attract and repel without touching. So they're a force field. Like electric charges, the strength of their interaction depends on the distance of the separation of the two magnets. Electric charges produce electrical forces, and regions called magnetic poles produce magnetic forces. So you have a magnetic pole, and that's what makes a magnetic field. Here in the picture, which interaction has the greater strength? The gravitational attraction between the scrap iron and Earth, or the magnetic attraction between the magnet and the scrap iron? So obviously, if this scrap iron is not falling down, then the magnet is doing more work to hold it up against gravity. Have you ever seen one of these in action? Well, this is the kind of thing you don't really see out here in the country. Just so you know, that's an electromagnet. So he's able to, the controller down there is able to turn that magnet off with the flip of a switch. And as soon as it's over the truck, he turns it off and all the iron falls into the truck. Then he goes over to that great big pile and picks up another load of iron. All right, here's a picture of an electromagnet coming in and picking up this V8 motor right off the back of the guy's truck for the scrapyard. Boom. And away it goes. And he just turns it off and it falls in. Okay, there's the operator. Here comes the electromagnet. He's going to pick out the scrap iron out of that load of junk material that somebody brought into the yard. Magnet comes down. He flips it on. All the iron gets picked up. All the other stuff gets left behind. And he takes that over to the scrap iron pile, turns the magnet off. Oh, we don't quite see it fall. And that's that. Okay. If you suspend a bar magnet from its center by a piece of string, it will act as a compass. The end that points northward is called the north-seeking pole. The end that points southward is called the south-seeking pole. More simply, these are called the north and south poles. All magnets have both a north and a south pole. For a simple bar magnet, the poles are located at the two ends. If the north pole of one magnet is brought near the north pole of another magnet, they repel. The same is true of a south pole near a south pole. If opposite poles are brought together, however, attraction occurs. Then we have our little parrot here with some really good advice. Let me blow that up. Beware of junk scientists who sell magnets to cure physical ailments. Claims for cures are bogus. Totally bogus. We need a knowledge filter to tell the difference between what is true and what seems to be true. The best knowledge filter ever invented is science. True that. Magnetic poles behave similarly to electric charges in some ways, but there is a very important difference. Electric charges can be isolated, but magnetic poles cannot. A north magnetic pole never exists without the presence of a south pole and vice versa. The north and south poles of a magnet are like the head and tail of the same coin. We'll figure out the why of this in section 3 or 4, but for now, just you have to know that you can never have a north pole of a magnet without having a south pole on the other end. That's always true. If you break a bar magnet in half, each half still behaves as a complete magnet. Wait for the picture. Break the pieces in half again, and you have 4 complete magnets. Even when you Your piece is 1 atom thick. There are 2 poles. This suggests that atoms themselves are magnets, which is true. So there we have the pole, north and south. You break it. Oops. And now you have a north and south and another north-south. Break it again and again and again and so on and so on and so on. Even an atom, when it gets down to a single atom after all those breaks, is going to have a north end and a south end. Does every magnet necessarily have a north and a south pole? Yes, just as every coin has 2 sides, a head and a tail. All right, here's the question. How do magnetic poles affect each other? If you're not sure about the answer, then you need to go back to the start of 36.1 and watch that section again. Moving on. Section 36.2, magnetic fields. The direction of the magnetic field outside a magnet is from the north to the south pole. Iron filings sprinkled on a sheet of paper over a bar magnet will tend to trace out a pattern of lines that surround the magnet. The space around a magnetic, in which a magnetic force is exerted, is filled with a magnetic field. A magnetic field. Once again, that's a force field, right? And so the shape of the field is revealed by magnetic field lines. So I'll show you a video of this in a moment, but you can see there's all these filings are basically tiny little dots, and they group together to show these lines. So there's the lines from north to south, and the south comes straight out there, and eventually it will loop all the way around and come back into the north on the other end. Magnetic field lines spread out from one pole, curve around the magnet, and return to the other pole. Right there you see the magnet, that's the magnet there. Put a piece of paper over it, and he's sprinkling the iron filings. They come out, they're tiny little bits. And as you sprinkle them out, then you give the paper a tap, and they line up. And now you can see them making the lines. You can even see how it's 3-dimensional. See how they stick up out of the paper there? And you can clearly see the North Pole and the South Pole. Oh, this is the North Pole because that was the side the North was pointing to. And it goes straight across the magnet, and then the lines come out and circle around. So one line makes a big loop that way and down this way. And they will even go out this way and way around. Does that make sense? Do you like that? All right, this is how you make a nail. There's a nail there, and she's rubbing a magnet along it to turn the nail into a magnet. Rub it again. There we go. Third time. And you put the nail on the plastic that's floating on the water. And so now the nail can turn to point towards north. And if we get away from her, look at the nail. There we go. The nail is now pointing towards the north. Did you ever do that when you were a kid? So here we have a magnet next to another magnet. There's a north and a south. Those sides are going to attract. You can see the magnet lines line up pretty much straight from one to the other. And the north and the north are going to repel. So they come in and then turn away. They turn to this south or they turn to that south. So that's how you get that weird X pattern in the middle. And then if you flip one magnet around, so now the norths are together, well, the lines come out and they get repelled from the north, so they go over here to the south. And here when they go up, they hit the north, and so they're going to repel around back into the south over here. Are you starting to see how these magnetic lines, the lines of force, just like the electric field lines, are working? Great. The direction of the magnetic field outside a magnet is from the north to the south pole. Where the lines are closer together, the field strength is greater. The magnetic field strength is greater at the poles. If we place another magnet or a small compass anywhere in the field, its poles will tend to line up with the magnetic field. So this is something I do in the classroom all the time. In fact, let's go find a video. I'm sure somebody's done it. Here we have a guy with an overhead transparency. He's got a bar magnet and then he's lining up these compasses around it. And you can see how all the compass line needles are pointing towards the north. So that's the north side of the magnet, and this is the south. Pretty tricky. All right, onward. Oh, so the end of section point 2. What is the direction of the magnetic field outside a magnet? If you don't know the answer to that question, then you should probably go back to the beginning of 36.2 and rewatch that section. 36.3. The nature of a magnetic field. A magnetic field is produced by the motion of electric charge. Okay, so now we're getting into the cause of what makes magnetism. Magnetism is very much related to electricity. Just as an electric charge is surrounded by an electric field, a moving electric charge is also surrounded by a magnetic field. And that's important. The electric charge has to be moving. If you have an electric charge and that's just sitting perfectly still, it doesn't have a magnetic field. Charges in motion have associated with them both an electric and a magnetic field. Charges in motion have associated with them both an electric and a magnetic field. Where is the motion of electric charges in a common bar magnet? So the magnet as a whole may be stationary, but it is composed of atoms whose electrons are in constant motion about atomic nuclei. This moving charge constitutes a tiny current, and that current produces a magnetic field. Remember, a tiny current. A current is a charge in motion, and that moving charge produces a magnetic field. Now, here's a picture of an electron, and it's orbiting the nucleus. Now, I don't know if you remember this from chemistry, but all electrons have a property called spin. Electrons can be thought of as spinning about their own axes like tops. So while this electron is moving around the nucleus, it's also spinning. Spin, spin, spin. They all do that. They're required to do that. You can't stop an electron from spinning. It's an inherent property. And this is what makes the magnetic field. Because this electron is spinning, that electron is now a charge in motion, and a magnetic field comes out of that electron. So you have a north field coming out, it loops around and comes back in the south field. So if you spin in the other direction, well, then the north will be on the bottom. So which way this electron is spinning, clockwise or counterclockwise, determines if the north pole is coming out the top or the bottom. A spinning electron creates another magnetic field. And actually, in most materials, the magnetic field due to the spinning of the electron predominates way stronger over the field, the magnetic field, due to the orbital motion. So 99% of the time, if you have a magnet, then it's going to be because of the electron spins are aligning. It's not that these are all orbiting in the same direction. The electron spin is what makes most of the magnetism, most of the time. Did you like that explanation? So this is the result. Every spinning electron is a tiny magnet. A pair of electrons spinning in the same direction make up a stronger magnet. But electrons spinning in opposite directions work against one another. Their magnetic fields cancel. We've got a nucleus and we've got 3 electrons that are orbiting around it. This electron is spinning clockwise. spinning, not rotating, spinning. So its north is up. This one also has the spin, so its north is up. But this electron is spinning counterclockwise, so its north is down. So what's the end result? This atom is barely magnetic because its electrons do not all have their spins pointing in the same direction. This is going to show us a better picture of what I mean there. Here's an electron, E for electron, minus because it's got a negative charge. And this arrow is going around showing that it is spinning clockwise. So the result of a clockwise spin is the magnetic field, which is the bar magnet, black for south, red for north, points up. And this is the gray line to show the magnetic field line coming out of the electron going this way. They come out of north and they go down to the south. Come out of the north, go down to the south. So that's how this electron has a positive magnetic spin. And this one, since it's rotating counterclockwise, is the opposite. So what happens if you take this magnet, north pointing up, and this magnet, north pointing down, and add them together? Well, you don't have much of a magnet after that, do you? And then this slide. Every spinning electron is a tiny magnet. A pair of electrons spinning in the same direction make up a stronger magnet. Electrons spinning in opposite directions work against each other, so their magnetic fields cancel. Now, most substances are not magnets because the various fields cancel one another due to the electrons spinning in opposite directions. Do you remember how electrons come in pairs? I'm going to talk about that in a minute. Let me get through this slide. In materials such as iron, nickel, and cobalt, however, the fields do not cancel one another entirely. An iron atom has 4 electrons whose spin magnetisms are not canceled. Each iron atom, then, is a tiny magnet. The same is true to a lesser degree for the atoms of nickel, cobalt, and several others. So an iron atom that has 4 electrons whose spin magnetisms are not canceled. That's where I go back to the beginning of this. All right. Do you remember that magnesium? Magnesium is element number 12. And you did this in chemistry. I'm not saying we're going to have a test on it tomorrow or anything like that. All I'm saying is that in chemistry, you did all this stuff with orbital diagrams. And all I'm saying is, does this ring a bell? Do you remember doing this? So there was the 1s2 shell, the 2s2 shell, 2p, 3s, 1s, 2s, 3s, and then the electrons came in pairs. You had one up and one down. Well, that up and down is this. The spin is up, so up is the magnetic field, and spin down means the magnetic field is pointing down. So that's what those arrows were about in this stuff. And do you remember there, 1s, 2s, 2p, do you remember filling these out in order and you had rules for how you put the arrows in? And what I thought would happen, he thought you'd skip 4s and you put them there, but no. The answer is you put 4s up and down, then you put one arrow up in these. Is this starting to ring a bell? And then this was the S shell is a sphere, the P shell are a pair of lobes. The D shell had 4 lobes, sometimes 2 of them made a ring. And then the F shell had 6 lobes, and they could make all kinds of different patterns. I'm not saying you have to know this, I'm just saying, does this ring a bell from chemistry? So that's where you had the S, P, D, and F shells. And S had 1 box, P had 3 boxes, D had 5, and F had 7. See how D has 5 boxes, S has 1, P has 3 boxes, and each box gets an electron. And you can have 2 electrons in a box, but the spins have to be opposite. And then you would fill them in like this, 3D, 4s, 3p. You'd start at the bottom and work your way up, 1s, 2s, 2p, 3s. And how do you figure out the order for this 1s, 2p stuff? Well, you did this. You would write down 1, 2, 3, 4, 5, 6, and then 2, 3, 4, 5, 6, then 3, 4, 5, 6, then 4. And the letters were decided by the chemists. They use S, P, D, F, and then G, blah, blah, blah. And you would write the arrows this way to figure out the order. So you would go 1s, follow the arrow, 2s, follow the arrow, 2p, 3s, follow the arrow. I'm not saying you have to know how to do this. I'm just showing you this so that you remember doing this in chemistry class. You did a whole bunch of this stuff. Okay? So now I want to come to the periodic table. And what did we say? Oh, I messed up my slide order. It's okay. Iron is the strongest magnet, then nickel and cobalt are also strong. So here's iron, Fe, and here's the shell. This, if you remember, was the D shell. Or was it the F shell? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is 5, SPD, the D shell. So if you go 1, 2, these filled up the first box, and then 1, 2, 3, 4. So this iron has 4 electrons, that the way the order goes, all 4 of those electrons are all pointing up, like this has 5. Well, nothing really has 5 ever. But it would be like 1, 2, 3, 4. So 4 ups in the iron make this the strongest magnet on the periodic table. And then cobalt is also very strong, and so is nickel. These are all in a row. Cobalt's a little weaker, and nickel's a little weaker after that. Some others that are really strong, neodymium. If you've ever played with magnets and you got the really good magnets, those are the neodymium magnets. I wish we were in class because I have some neodymium magnets you can play with, and you can feel the difference as soon as you have it in your hands. The neodymium magnets are quite a bit stronger than the iron magnets. Now, part of that is because it's easier to manufacture these in a special way to make a really strong magnet. What else? Oh, I don't remember any other. There's others elements out here that are somewhat magnetic. I just can't remember them often. There's one, gadolinium. That's one of them. Okay. Most substances, we covered that. So, how is a magnetic field produced? That's what you need to know coming out of this section. A magnetic field is produced because electrons have a spin, and if the electrons all have spins pointing in the same direction, that makes for a strong magnet. So the end result is not that tough, but I wanted to give you the correct background on all of that. Now, we are going to keep going. Like I said, I want to cover a lot of material on Friday. We won't do a lab on Friday, and then we will have more time next week to get ready for the final. So we're going to keep going. Thank you. 36.4 is magnetic domains. Permanent magnets are made by simply placing pieces of iron or certain iron alloys in strong magnetic fields. That's how you make a magnet. The magnetic fields of individual iron atoms are not strong. Are strong. The magnetic fields of individual iron atoms are strong. Interactions among adjacent iron atoms cause large clusters of them to line up with one another. And these clusters of aligned atoms are called magnetic domains. Now, each domain is perfectly magnetized and is made up of billions of aligned atoms. and the domains are microscopic. Remember, a mole of material has 10 to the 23 atoms in it. So this is, you need not just a microscope, but sometimes you need an electron microscope to see the small iron grains in a piece of iron. And so all the iron atoms in this grain, which is a kind of a rectangle shape, are pointing in this direction. This five-sided is they're all in that direction. They're all in this direction. All right, moving on. The difference between a piece of ordinary iron and an iron magnet is the alignment of domains. In a common iron nail, the domains are randomly oriented. But when a strong magnet is brought nearby, there is a growth in size of domains oriented in the direction of the magnetic field. The domains also become aligned, much as electric dipoles are aligned in the presence of a charged rod. From back in electricity. When you remove the nail from the magnet, thermal motion causes most of the domains to return to a random arrangement. Most, but not all. So permanent magnets are made by simply placing pieces of iron, or certain iron alloys, in strong magnetic fields. Another way of making a permanent magnet is to stroke a piece of iron with a magnet, like we saw that feature in the video when we made a compass. The stroking motion aligns the domains in the iron. Now, a stroking motion aligns them because you're using a magnet to stroke the iron, but if you drop it, if a permanent magnet is dropped or heated, some of those domains are jostled out of alignment and the magnet becomes weaker. So, here's what it looks like. The arrows represent domains. We're not going to draw little greens in there because it just clutters it up. Where the head is a north pole and the tail a south pole. Poles of neighboring domains neutralize one another's effects, except at the end. So here's an ordinary piece of iron, everything pointing in a random direction. If it has a little bit of magnetism to it, they kind of point the same way. But if you put it in a magnetic field and then tap it and move it around a little, you can get all the domains pointing in the same direction. And then you have a really strong magnet. And like we said from before, if you cut it in half, you still have a north-south on each end. Iron filings, sprinkled on paper that covers a magnet, were not initially magnetized. Why then do they line up with the magnetic field of the magnet? Because the magnet makes those iron filings magnetized. And now all those little iron filings that are getting magnetized attract each other and they line up in the lines that we could see on the paper. Does that make sense? Great. Oh, I forgot the written answer. Domains align in the individual filings, causing them to act like tiny compasses. The poles of each compass are pulled in opposite directions, producing a torque that twists each filing into alignment with the external magnetic field. That's a different way of saying it. All right, so after that section is done, the question is, how can you make a permanent magnet? If you're not sure about that answer, you should go back and rewatch some of that section. Okay.